Hey everyone, welcome to your Postgres video. My name is Caleb, and this video is going to give you everything you need to get started with the Postgres database. This is a great database to get started building applications. It's going to give you the ability to use this in a production environment without having to pay money. It's all open source, and overall getting started with Postgres is very easy. You can read more about Postgres at their website, postgresql.org, and you can see how is Postgres licensed. There's no fee even for use in commercial software products. So you can start building your application with Postgres, and then if you decide to launch it and you're actually making some money, you don't then have to go pay a bunch of money for permission to use the database in a commercial setting. So to get started, go to the download page for Postgres. Hey everybody, welcome to your Postgres video. My name is Caleb, and this video is going to give you everything you need to get started with the Postgres database. This is a great database to get started building applications. It's going to give you the ability to use this in a production environment without having to pay money. It's all open source, and overall getting started with Postgres is very
PostgreSQL, the most trusted name in open source relational databases. Its development dates all the way back to 1986 at UC Berkeley, under the direction of Michael Stonebraker. Like other pure relational databases, it stores data in tables, columns, and rows, and uses structured query language to read and write data. However, Postgres is technically an object relational database, which means it can create its own custom data types to store objects with properties and support advanced features like inheritance and polymorphism. When writing data, it runs fully ACID compliant transactions, but also adds its own special sauce called multi-version concurrency control, which gives each transaction a snapshot of the database, allowing multiple transactions to run at the same time without traffic jams or locks. Developers also love its extensibility. Queries can be reused by writing stored procedures, and it even supports languages beyond SQL like Python and C. And it has a robust ecosystem of extensions, like PostGIS to provide geospatial data for apps like Uber, or Citus to shard and distribute the database to any scale, or PG embedding to give AI chatbots long-term memory, and the list goes on. To get started, you can download and install it locally, or better yet, use a free cloud database like Neon, which provides auto-scaling out of the box and a nice UI to manage your data, in addition to a bunch of other advanced features like branching. Create a new database, then head over to the SQL editor to run your first query, or connect it to your IDE with an extension like SQL Tools. We could get started by creating a new table, but because this is an object relational database, let's begin by creating a custom data type, which defines the structure of an object with corresponding properties and types. What's awesome about Postgres, though, is that we have more exotic data modeling options. Like arrays can be used by putting brackets in front of a type, then make it a two-dimensional array by adding another set of brackets. We also have JSON data types to handle unstructured data, and even key value pairs with extensions like HStore. Now that we have this custom type, we can use it within one or more tables, like one table for programmers and another for designers. Once the table is created, we can then use an insert statement to add a row of data into it. Notice the use of a double colon to cast a string into JSON or HStore types. And now finally, we can read the data with a select statement that uses dot notation to access the properties on our custom object. Every table has a unique primary key, and we can create relationships by storing the primary key from one table as the foreign key on another, like a programmer might own many Lambos. We can then find those Lambos by doing a join query that compares the programmer's ID to the Lambo's owner ID. This has been PostgreSQL. Modern web development sucks. We have amazing tools that solve every problem, and technically, it's never been easier to build a billion-dollar failed app idea. The problem is that by the time you deploy it, you end up paying 20 different YC-backed startups to use their fancy shovels. You think you need an in-memory cache database to handle your load of 5 users, you need a cron service, you need authentication, performance monitoring, analytics, serverless functions, and the list goes on. It's no coincidence that America's homeless population started to rise immediately after the release of Next.js in 2016. But what if I told you you could throw all of these shovels in the incinerator and use nothing but PostgreSQL? Yes, the relational database, to achieve 90% of your web development needs. In today's video, we'll look at 11 useful, unorthodox, and just plain weird ways to use Postgres. By the end of it, we will have built a full stack application using nothing but an open source database. But first of all, what makes Postgres special, and why not use something like MySQL or SQLite? Well, out of the box, Postgres provides advanced data types like binary JSON, arrays, key value stores, and even geometric types to define shapes. But more importantly, it's extensible, and you can even create your own custom data types. Over the years, this has led to a massive ecosystem of extensions where developers have given it all kinds of crazy new features. It's just like modding a game where you take something that sucks like Civilization 7 and install a bunch of mods to make it playable. Now, before we get into the first example, I first want to warn you that just because you can do something in Postgres doesn't mean you should. Before you go and cancel all your shovel subscriptions, don't forget to think critically and make sure you use the right tool for the job. One of the great debates among web developers is SQL versus NoSQL, and one of the key selling points for NoSQL is that you can work with unstructured data, like objects with dynamic data that might be different for each record. You can't do that in SQL because every table has a fixed schema. Well, actually, that's not true because Postgres supports binary JSON. In this query, you'll notice how we create a table with a JSON-B type and then insert some values into it as raw JSON strings. So pretty cool, and believe it or not, we can actually query this data now. We can use a select statement followed by a where clause and then this arrow syntax to filter and access fields inside this unstructured data. That feature is built right into Postgres, but now we're going to implement some really crazy stuff thanks to extensions. First though, you might be wondering, where do I get a Postgres database? It's free and open source to host locally, but an even easier option is Neon, the sponsor of today's video. They may not condone all the crazy stuff I'm showing, like branching, which allows you to easily create different data workflows for development, testing, and production, and will automatically scale up with zero effort as your app grows. Give Neon a try for free right now using the link below to create a Postgres database. Then take your connection details to a VS Code extension like SQL Tools and connect to it locally. And now we're ready to do some really crazy stuff with extensions. Developers only want one thing, and it's disgusting: a cron job, which is code that runs on a schedule. Now, normally you would have to edit the cron tab file in Linux to achieve this, or pay a SaaS to do it for you, but Postgres will actually give you a cron job for free. If we install the pgcron extension, we can then write a SQL statement that runs a cron schedule. Give it a name, define the schedule, and then it will run the SQL statement on that schedule. Like you might want to delete or aggregate a bunch of data on a daily basis. That's cool, but another thing you think you might need but probably don't is an in-memory cache database, like Redis or Memcache. Well, in Postgres, you can create your own poor man's Redis by using an unlogged table as a cache. This prevents write-ahead logging, where changes to the database are written to a log file before being applied to data files, and that provides the D for durability and ACID, and that means if your server crashes unexpectedly, committed transactions will not be lost. However, you don't really need that for a cache, and disabling it provides better performance. Then you can update the Postgres config to store it in a shared buffer, which will keep the data highly available in RAM, and then summon the auto-vacuum daemon to avoid bloat, and maybe throw in pgcron to automatically delete any entries with an expired time to live. But this wouldn't be a proper Fireship video if I didn't mention AI, and if you're building an AI app that uses RagStack, you might consider paying for a vector database, but what you could do instead is just install the pgvector extension. It provides a vector data type that allows you to store multi-dimensional data. Then you can do things like make a query for nearest neighbors based on L2 distance, and you can even take things a step further with the PGAI extension. Not only does it handle vector embeddings, but it allows you to load your own data set and vectorize it all entirely in SQL code. But speaking of vectors, a more traditional feature you might need is a full text search engine, where users type into a search box and get results even if they have typos. Postgres actually has built-in support for this with the TS vector type. It'll take a string like this and break it up into a bunch of smaller parts. Then we can create a generalized inverted index for better performance, which gives us the ability to then rank and query the most likely results from the data using double at, which is the text search operator. And now you don't have to pay for expensive tools like Algolia or Elasticsearch. If you're sick of writing SQL code though, one thing you might do instead is use GraphQL. The magic PG GraphQL extension can transform your database into a GraphQL API, and that makes it incredibly easy for any programming language to understand and query your database. Just add the extension and then start writing GraphQL resolvers directly in your SQL code. And best of all, no additional servers, libraries, or paid SaaS middlemen are required. But what if you're building a real-time application using tools like Firebase or Supabase? That's a difficult feature to roll out on your own, but a library called Electric SQL fixes this. It's not a PG extension, but rather a sync layer, which would sit in between your database and your front-end code to ensure that the end user always has fresh data. And that means you don't have to mess around with WebSockets or write a bunch of broken code to automatically fetch data when it changes. And as an added bonus, it works great with Neon. But another thing developers like to brag about is rolling their own auth, usually by writing some crappy JavaScript instead of paying a SaaS to do that for them. But real men roll their own auth entirely in Postgres, and that's possible when you combine a couple of extensions like PG My dad used to tell me, use the right tool for the job, and not vice versa. When it comes to app development, choosing the right database is one of the single most important decisions that you'll ever make. In today's video, we'll look at 7 different database paradigms, along with some databases you've probably heard of and some others that you haven't. We'll look at how they work from a technical perspective, but most importantly, we'll try to understand what they're best used for, because my dad also used to tell me, don't bring a knife to a gunfight. If you're new here, like and subscribe, and also check out my new Top 7 playlist for more videos like this. Our list will start from the most simple type of database and gradually become more complex as we get to number 7. And that brings us to our first paradigm, the key-value database. Popular databases in this space include Redis, Memcached, and etcd. The database itself is structured almost like a JavaScript object or Python dictionary. You have a set of keys where every key is unique and points to some value. In Redis, for example, we can read and write data using commands. We use the set command, followed by a key and a value to write data, then the get command to retrieve that data in the future. In the case of Redis and Memcached, all of the data is held in the machine's memory, as opposed to most other databases that keep all their data on the disk. This limits the amount of data you can store, however it makes the database extremely fast because it doesn't require a round trip to the disk for every operation. In addition, it doesn't perform queries, joins, or anything like that, so your data modeling options are very limited, but again, it's extremely fast, like sub-millisecond fast. You wouldn't want to use a key-value store for your main app data. Most often, they're used as a cache to reduce data latency. Apps like Twitter, GitHub, and Snapchat all use Redis for real-time delivery of their data. There are other use cases beyond caching, like message queues, PubSub, and gaming leaderboards, but more often than not, key-value databases are used as a cache on top of some other persistent data layer. Now, a database that only supports key-value pairs is obviously pretty limited, and that brings us to the wide column database. Popular options in this family include Cassandra and HBase. A wide column database is like you took a key-value database and added a second dimension to it. At the outer layer, you have a key space, which holds one or more column families, and each column family holds a set of ordered rows. This makes it possible to group related data together, but unlike a relational database, it doesn't have a schema, so it can handle unstructured data. This is nice for developers because you get a query language called CQL that's very similar to SQL, although much more limited and you can't do joins. However, it's much easier to scale up and replicate data across multiple nodes. Unlike an SQL database, it's decentralized and can scale horizontally. A popular use case is for scaling a large amount of time series data, like records from an IoT device, weather sensors, or in the case of Netflix, a history of the different shows you've watched. It's often used in situations where you have frequent writes, but infrequent updates and reads. It's not going to be your primary app database. For that, you'll need something more general purpose, like a document-oriented database. Popular options in the document family include MongoDB, Firestore, DynamoDB, CouchDB, and a few others. In this paradigm, you have documents, where each document is a container for key value pairs. They're unstructured and don't require a schema. Then the documents are grouped together in collections. Fields within a collection can be indexed, and collections can be organized into a logical hierarchy, allowing you to model and retrieve relational data to a pretty significant degree. They don't support joins,
set are vastly larger than the other. The difference can create inconsistency when we process the data. To fix this, we use a technique called normalization. There are multiple types of normalization, but in this video, we will focus on 2 of them. Let's start with min-max normalization. This one is extremely simple. We scale all the values so that they fall within a specific range, typically from 0 to 1. Each feature is scaled proportionally, so the relative difference between data points are preserved. The formula for min-max normalization looks like this. Here, xi is single data point for one feature, and min x and max x are the minimum and maximum values of that feature in the dataset. Remember, each feature has its own minimum and maximum, so this scaling is done separately for every feature. This ensures that all features are transformed to the same range without mixing their scales. If you want to scale a feature to a custom range, say A to B, we can generalize the formula like this. This method of normalization is simple to understand and easy to implement, but it is not commonly used in neural networks. Now let's look at a more practical method called standardization, also called z-score normalization. This method is commonly used in neural networks. Suppose we have a dataset with features that have uneven scales. The first step in standardization is to center the data around mean. In other words, we sift the data so that the mean of each feature becomes 0, effectively moving the center of the data to the origin of the graph. At the same time, even every data point keeps its relative position with respect to the others. The formula for standardization is simple. First, we calculate the mean of the feature. Then, for each data point, we subtract the mean and assign the result as the new value for that data point. This step centers the data around mean. This step centers the data around 0. In practice, data science libraries like NumPy or Pandas use vectorization to efficiently perform these operations on entire datasets at once. The next thing to consider is that some features may have a much larger variance than others. If we leave it like this, the feature with large variance can dominate the learning process. To fix this, we scale the data so that each feature has a variance of 1. This ensures that all features contribute equally to the model, preventing any single feature from overpowering the other. The formula for making the variance 1 looks like this. First, we calculate the variance of each feature. Since we have already centered the data around mean, so the mean is 0, we can simplify the variance formula by removing the mean term. Next, we divide each data point by the standard deviation. And remember, the standard deviation is just the square root of the variance. After this step, each feature has a variance of 1, and the data is both centered and scaled, making it ready for most machine learning algorithms, including neural networks. Now, one important question is, why do we actually do this? Let's understand this with an example. Imagine we are only using 2 parameters, w and b. On the left, we have the unnormalized data, and on the right, we have the normalized dataset. On the left, you can see that the data is highly skewed and uneven, with features on very different scales. This asymmetry makes optimization algorithms like gradient descent unpredictable. The gradient can move very slowly along one direction and too quickly along another, requiring many iterations to converge to the optimum. On the right, after normalization, the data becomes more symmetrical and balanced. This allows gradient descent or any other optimization algorithm to converge faster and more reliably because all features contribute more evenly to the updates. In short, normalizing makes optimization more efficient, stable, and predictable.
Question number.
This is not a coincidence. Hello people from the future, welcome to Normalized Nerd. I know it's been a year since I uploaded my last video, but as I mentioned in my community post, a lot of things happened in my life in the past year, and I was super busy with it. But finally, I'm here.
Max, Soft, Max, StatQuest. Hello, I'm Josh Starmer, and welcome to StatQuest. Today we're going to talk about Neural Networks Part 5, Argmax and Softmax. Note, this StatQuest assumes that you already understand the main ideas behind neural networks, the main ideas behind backpropagation, and how neural networks work with multiple input and output nodes. If not, check out the quests. The links are in the description below. In the StatQuest on neural networks with multiple input and output nodes, we had a fancy neural network that used petal and sepal widths to predict iris species. The neural network made predictions with crinkled surfaces for setosa, versicolor, and virginica. Then we
In this video, I want to try to give you a deeper understanding for how the softmax function works, and hopefully I'll be able to show you something about it that you hadn't realized before. So in machine learning, the softmax function is often used to transform the outputs from the last layer of your neural network into probabilities. And these might be probabilities for classifying a certain type of image, for example. So here, if we imagine these 4 dots were the outputs from our neural network, and they were trying to classify, for example, what type of fruit was in that image, and let's say we only had 4 classes. Here, the red is for a red apple, orange is for an orange, green is for a green apple, and blue is for a blueberry. So if this were the outputs from our model, then the model would most likely think the picture is of a blueberry. Basically, the farther to the right the output is for a certain class, the more likely the model thinks the input data is for that class. And the outputs from the model can be anywhere on the number line, from in between negative infinity to infinity. So the question is, how do we convert those numbers into probabilities? And that's what the softmax function can be used for. So how the softmax function works is it takes each of these values, and then it takes this function e to the x, and it sees where each of these points would fall on this function. Then we take the height of each of these lines corresponding to each class, and we add them up to get our total height, which is this dashed line here. You can also see on the right here, each of these bars will be the height of each of these lines, and then this bar will be the total of all of them added together. And then our final probabilities for each of these classes will just be the height of its line divided by the total height of all these heights added together. So we can see as we move around these input points, not only does moving this point change the height of this line, but it also changes the height of the total. So to better see how this is actually going to change the probabilities of each of these points, we can squash this graph down so that the height of the total always has a height of 1. So I've added that down here below. Basically takes this portion of the graph and we'll just squash it down. So now this dashed line is always 1 above this baseline. Then each of these heights of the colored dashed lines will be the probability for that class. So now we can see if we move around one of these inputs on this bottom graph, the total height will remain the same, and the graph will just be more or less squashed depending on what the total height was up here. So now if we just expand this graph a bit, so it makes it a bit easier to see what's happening down here, we might ask, as we move one of these points, what type of path does it follow? If we plot its path, we can see that it is the sigmoid function. And basically, whatever point is moving, that point will follow a sigmoid function. So here's the red one, here's the orange, and all the other ones will adapt to the change in that value. And here's green, and here is the blue. And here we can see the paths that all the points follow as the red dot changes. So these dots with the holes in them will have the same exposition as the red line, but they'll have the same height as the height for their class. And as we move the red dot, we can see that not only does its height move in a sigmoid function, but so do the heights of the other classes. They're just moving in the opposite direction. So as red moves up in a sigmoid pattern, all the other classes will move down in a similar sigmoid pattern, just scale down to what the height of that class would be if red basically had a height of 0. So that's the first insight. If we increase the input value for a certain class, its output probability will move along an increasing sigmoid path. And all the other classes will move in a decreasing sigmoid path. Now another key aspect of the softmax function is that if you shift all the inputs by the same amount, it actually won't change the output probabilities. So here we can see
Arg, Max, Soft, Max.
you don't like silly songs, that's okay. StatQuest. StatQuest, check it out. Talking about machine learning, yeah. StatQuest, check it out. Talking about cross-validation, yeah. StatQuest.
Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about cross-validation and it's going to be clearly explained. Okay, let's start with some data. We want to use the variables, chest pain, good blood circulation, etc., to predict if someone has heart disease. Then, when a new patient shows up, we can measure these variables and predict if they have heart disease or not. However, first we have to decide which machine learning method would be best.
Gonna start this stat quest with a silly song. But if you don't like silly songs, that's okay. StatQuest.
Hello, I'm Josh Starmer, and welcome to StatQuest. Today we're going to do a gentle introduction to machine learning. Note, this StatQuest was originally prepared. Here's another silly example of machine learning. Imagine we measure
Hurricane Florence came by while I was working on StatQuest. Dark clouds filled the sky, but that didn't stop StatQuest. StatQuest.
Hello, I'm Josh Starmer, and welcome to StatQuest. Today we're going to be talking about some machine learning fundamentals, bias and variance, and they're going to be clearly explained. Imagine we measured the weight and height of a bunch of mice and plotted the data on a graph. Light mice tend to be short, and heavier mice tend to be taller. But after a certain weight, mice don't get any taller, just more obese. Given this data, we would like to predict a mouse height given its weight. For example, if you told me your mouse weighed this much, then we might predict that the mouse is this tall. Ideally, we would know the exact mathematical formula that describes the relationship between weight and height. But, in this case, we don't know the formula, so we're going to use two machine learning methods to approximate this relationship. However, I'll leave the true relationship curve in the figure for reference. The first thing we do is split the data into two sets, one for training the machine learning algorithms and one for testing them. The blue dots are the training set, and the green dots are the testing set. Here's just the training set. The first machine learning algorithm that we will use is linear regression, aka least squares. Linear regression fits a straight line to the training set. Note, the straight line doesn't have the flexibility to accurately replicate the arc in the true relationship. No matter how we try to fit the line, it will never curve. Thus, the straight line will never capture the true relationship between weight and height, no matter how well we fit it to the training set. The inability for a machine learning method, like linear regression, to capture the true relationship is called bias. Because the straight line can't be curved like the true relationship, it has a relatively large amount of bias. Another machine learning method might fit a squiggly line to the training set. The squiggly line is super flexible and hugs the training set along the arc of the true relationship. Because the squiggly line can handle the arc in the true relationship between weight and height, it has very little bias. We can compare how well the straight line and the squiggly line fit the training set by calculating their sums of squares. In other words, we measure the distances from the fit lines to the data, square them, and add them up. Psst. They are squared so that negative distances do not cancel out positive distances. Notice how the squiggly line fits the data so well that the distances between the line and the data are all zero. In the contest to see whether the straight line fits the training set better than the squiggly line wins. But remember, so far we've only calculated the sums of squares for the training set. We also have a testing set. Now let's calculate the sums of squares for the testing set. In the contest to see whether the straight line fits the testing set better than the straight line wins. Even though the squiggly line did a great job fitting the training set, it did a terrible job fitting the testing set. In machine learning lingo, the difference in fits between datasets is called variance. The squiggly line has low bias since it is flexible and can adapt to the curve in the relationship between weight and height. But the squiggly line has high variability because it results in vastly different sums of squares for different datasets. In other words, it's hard to predict how well the squiggly line will perform with future datasets. It might do well sometimes, and other times it might do terribly. In contrast, the straight line has relatively high bias, since it cannot capture the curve in the relationship between weight and height. But the straight line has relatively low variance, because the sums of squares are very similar for different datasets. In other words, the straight line might only give good predictions and not great predictions, but they will be consistently good predictions. Bam! Oh.
Yes, you can understand entropy. Hooray! StatQuest.
Hello, I'm Josh Starmer, and welcome to StatQuest. Today we're going to talk about entropy for data science, and it's going to be clearly explained. Note, this StatQuest assumes that you are already familiar with the main ideas of expected values. If not, check out the
Today we're gonna talk about what to expect when you're expecting a value. StatQuest.
Hello, I'm Josh Starmer, and welcome to StatQuest. Today we're going to talk about expected values, and they're going to be clearly explained. Let's start by taking a trip to the magical place called Statland. The quest. Intro. Entropy is used for a lot of things in data science. For example, entropy. Once we get to Statland, our friend, StatSquatch, says, "Hey, I bet the next person we meet has heard of the movie Troll 2. And we say, "Are you kidding me? Troll 2 is one of the worst movies ever made. Why would anyone know about it?" And then StatSquatch says, "I bet you $1 that the next person we meet has heard of the movie Troll 2. So we think to ourselves, good thing we recently asked everyone in Statland if they'd heard of the movie Troll 2. Here's the data. There are two types of people in Statland. People that have heard of the 1990 movie Troll 2, and people who have never heard of Troll 2. In other words, there isn't anyone who has both sort of heard of Troll 2 and sort of hasn't heard of Troll 2. Each person in Statland is in one group or the other. 37 of the people in Statland have heard of Troll 2, and the remaining 176 people in Statland have never heard of Troll 2. That means there are 213 people living in Statland. So Statland is not a huge place. Looking at the raw numbers is useful because they tell us that Statland is pretty small, and that whatever analysis we do only applies to a handful of people. That said, by looking at the numbers, we can get a general sense of the trends in Statland. In this case, we see that most of the people in Statland have never heard of Troll 2. But, at a glance, it's not super obvious how the number of people who have never heard of Troll 2 relates to the total population of Statland. The good news is that we can make this relationship super obvious by calculating probabilities. So let's calculate the probabilities of people in Statland that have and haven't heard of Troll 2. If we want to know the probability that a randomly selected person in Statland has heard of Troll 2, we simply divide the number of people that have heard of Troll 2, 37, by the total, 213. And that gives us 0.17. That means the probability that a randomly selected person in Statland has heard of Troll 2 is 0.17, which is relatively low. Likewise, the probability that a randomly selected person in Statland has never heard of Troll 2 is 0.83, which is relatively high. Now, remember that bet our friend StatSquatch wanted to make? I bet you $1 that the next person we meet has heard of the movie Troll 2. The good news is that we can use these probabilities to decide if we should agree to the bet. So let's move the probabilities to the top so we can focus on them. Now, if the next person we meet has heard of Troll 2, then we will lose the bet. And that means we will lose $1. So let's put -1 here to represent the outcome of losing $1 if we meet someone who has heard of Troll 2. In contrast, if the next person has not heard of Troll 2, then we will win the bet. And that means we will win $1. So let's put 1 here to represent the outcome of winning $1 if the next person we meet has not heard of Troll 2. So the left side of this table tells us that the probability we will lose $1 is 0.17. And the right side tells us that the probability that we will win $1 is 0.83. In other words, the probability that we will win $1 is much higher than the probability that we will lose $1. And that makes it seem like it would be a good idea to accept the bet. However, even though there is a high probability that we will win the bet, there is still a low probability that we will lose. And no one likes to lose money. So we say, can we make this bet 100 times, or is this just a one-time offer? And our friend StatSquatch says, we can make this bet 100 times. Now, if we make this bet 100 times, we will probably win some and we will probably lose some. And we can use this table to predict how much we will win and lose. If we make this bet 100 times, we can approximate how many times we will lose by multiplying the probability we will lose, 0.17, by 100. And if we do the math, we get 17. So that means we expect to lose about 17 times in 100 bets. Since we will lose $1 each time we lose the bet, we can estimate the total amount of money we will lose by multiplying the number of times we expect to lose by -1. So this whole term represents how much money we expect to lose in 100 bets. And when we do the math, we get -17, and that means we expect to lose about $17. Wah wah. Now, since we can make the bet 100 times, we can approximate how many times we will win by multiplying the probability we will win, 0.83, by 100. When we do the math, we see that we expect to win about 83 times. Since each time we win the bet, we will win $1, we can estimate how much money we will win by multiplying the number of times we expect to win by 1. So this whole term represents how much money we expect to win in 100 bets. And when we do the math, we see that we expect to win $83. Now that we have a term for the expected amount of money lost, and a term for the expected amount of money won, we can add the two terms together to find out the total of how much we expect to win or lose. And when we do the math, we see that we expect to gain approximately $66 after 100 bets. However, we can also calculate the average amount of money we will gain per bet by dividing everything by the number of bets, 100. Doing the math gives us 66 divided by 100, which is 0.66. So, on average, we expect to gain 66 cents every time we bet. Note, even though I win or lose $1 each time I bet, on average, I expect to gain 66 cents each time. In statistics lingo, 66 cents is the expected value for the bet. Bam! Using fancy statistics notation, we could write E of bet equals 0.66. Or, if we wanted to make it look even more cryptic and more in line with what you might find in a textbook, we could write E of x equals 0.66, where x represents the bet. Now let's talk about why I left this messy math in the middle of everything. Since we are multiplying each probability by the number of bets, 100, and dividing by the number of bets, 100, then all of the values that represent the number of bets, 100, cancel out. And we're left with the probability that someone in Statland has heard of Troll 2 times the outcome, -1, plus the probability that someone has not heard of Troll 2 times the outcome, 1. And when we do the math, we get the exact same thing we got before, 0.66. Thus, the expected value represents what we would expect per bet if we made this bet a bunch of times. Note, we can rewrite the expected value using fancy sigma notation. Using -1, plus the probability that someone has not heard of Troll 2 times the outcome, 1. And when we do the math, we get the exact same thing we got before, 0.66. Thus, the expected value represents what we would expect per bet if we made this bet a bunch of times. Note, we can rewrite the expected value using fancy sigma notation. Using fancy sigma notation, the expected value, E of x, is the sum of each outcome, x, times the probability of observing each outcome, x. So, for the first term, heard of Troll 2, the outcome is -1, and the probability of observing the outcome is 0.17. So we multiply those values together. Then the sigma tells us to add that term to the term for not heard of Troll 2. Now the outcome is 1, and the probability of observing the outcome is 0.83. So, either way we do the math, we get 0.66. That means that if we can make this bet a bunch of times, even though we will lose some of the time, we should make money in the long run. Double bam. Now imagine StatsWatch saying, for 0.66. Thus, the expected value represents what we would expect per bet if we made this bet a bunch of times. Note, we can rewrite the expected value using fancy sigma notation. Using fancy sigma notation, the expected value, E of x, is the sum of each outcome, x, times the probability of observing each outcome, x. So, for the first term, heard of Troll 2, the outcome is -1, and the probability of observing the outcome is 0.17. So we multiply those values together. Then the sigma tells us to add that term to the term for not heard of Troll 2. Now the outcome is 1, and the probability of observing the outcome is 0.83. So, either way we do the math, we get 0.66. That means that if we can make this bet a bunch of times, even though we will lose some of the time, we should make money in the long run. Double bam. Now imagine StatsQuatch saying, because it is relatively rare for someone in Statland to have heard of Troll 2, I will pay you $10 if the next person we meet has heard of Troll 2, but if they have not, you pay me $1. Will we win money or lose money if we can make this bet a bunch of times? Let's calculate the expected value to find out. The outcome for when someone has heard of Troll 2 is 10 because we will gain $10. And the outcome for when someone has not heard of Troll 2 is -1 because we will lose $1. So these are the two outcomes. Now let's calculate the expected value. The expected value is the sum of each outcome times its associated probability. So let's start by plugging in the numbers for heard of Troll 2. First, the outcome, x, is 10, and the probability of observing that outcome is 0.17. Now we add the term for never heard of Troll 2. The outcome, x, is -1, and the probability of observing that outcome is 0.83. Now we just do the math, and the expected value is 0.87. And that means we expect to gain, on average, 87 cents every time we make this bet. And that means StatsQuatch is the worst gambler ever. Triple bam. Note, in this StatQuest, we've only talked about how to calculate expected values for discrete events, like whether or not someone has heard of Troll 2. However, we'll talk about how to calculate expected values for continuous events, like how much time passes between text messages on your phone, in another StatQuest. Lastly, if you watch this video hoping to learn exactly why we divide the sample variance by n-1, just know that this is the first of several steps to that answer, and we'll get there someday soon. Now it's time for some shameless self-promotion.
PyTorch or TensorFlow. Both are leading deep learning frameworks, and they both have pros and cons, so let's get into it. PyTorch, developed by Meta AI, dominates research, with 60% of published papers using it as of June of 2024, and people love its dynamic computational graph, intuitive model building, and seamless integration with Python tools like NumPy. The fact that it's Pythonic also helps to make it more useful for a wider audience, which means that it has an excellent ecosystem of models and libraries for PyTorch users to tap into. TensorFlow, on the other hand, developed by Google, is generally considered to be the industry standard for production environments. It offers robust deployment capabilities through TensorFlow serving and strong cloud service integration too. TensorFlow's comprehensive tooling includes TensorBoard for visualization, TensorFlow Lite for mobile deployment, and TensorFlow JS for web deployment. It also supports hardware acceleration through GPUs and TPUs, ensuring high performance in large-scale environments. PyTorch or TensorFlow, both are leading deep learning frameworks.